Good morning, pads. So I want to talk about the very practical application of deep learning algorithms to DoD's large modeling and simulation projects that are happening right now. So for those of you who need a little refresher on the DoD modeling and simulation, they typically categorize their simulation and training efforts into four categories. The events are either live, virtual, constructive, or game-based. Live means real soldiers with real equipment out in the field doing real activities, but minus the bullets. Virtual means those same soldiers sitting in the mock-up of a vehicle or a helicopter or some kind of device doing their jobs with a digital simulation. Constructive is a different kind of digital simulation that represents the battlefield from kind of a God's eye view and allows the leaders and commanders to make strategic decisions about how to move their forces around in a city or around on the battlefield. And then games are essentially the same as virtual simulation, but you don't build them a cockpit. You just give them a gaming computer and that's all the hardware they get. So all of these simulations are used to train either dozens or hundreds or maybe even thousands of soldiers simultaneously. And in the process of doing that, they're representing the virtual world at the sub-second level, constantly computing what comes next, what just happened, and usually publishing that information onto the network so that it can be shared with other computers, like in a multiplayer game, and can also be collected by people who are going to assess their performance when it's all over. So that makes them a huge data generator. And that data falls into at least 7 different categories. I won't go through the 7 categories. You can read more about them in the paper itself. But that data is either what's happening during the simulation, data that was prepared before the simulation started that represents the scenario and the terrain and the weapons and all of that, or data that was collected that's analyzed and assessed after the simulation happened. General categories. But there's huge gigabytes worth of data in every one of those categories. And the good thing about simulations being these huge data generators and data consumers is that it makes them an ideal candidate for applying deep and machine learning algorithms. Deep learning algorithms and machine learning appear to be smart because they can process thousands of instances of data, millions of instances of data, and find patterns that they can repeat back to you. And therefore, they look like they know what they're doing in the same way that a human knows what it's doing. But these algorithms can't function if they don't have those huge volumes of data. And DoD simulations are an ideal generator of those huge volumes of data to make deep learning work in some way. So I want to use the current Army synthetic training environment, which is the largest ongoing simulation project amounting to multiple hundreds of millions of dollars that's underway right now as an example for how to apply this. In that project, they envision that the training process has 4 phases. There's the planning phase, the preparation phase, the execution phase, and the assessment phase. In the planning phase, leaders get together and decide what a unit or a group of soldiers needs to be trained on. Maybe a new mission that they're going to face in the future, maybe skills that they need to develop that they're not completely proficient at right now, or maybe refreshers of things that they're supposed to know and you want to find out if they still know how to do it. And that planning takes place in kind of a whiteboard and map environment where they get the big idea of what they want represented, where it should happen, how many units should be involved, what kind of weapons should they be equipped with, et cetera, et cetera. What should the enemy be doing? And once they're done, they hand that off to an army of data entry people. And those people take that big plan and turn it into a digital database that contains all of the information that you would need to represent a city or the terrain or trees and all of the units and all of the soldiers and all of the weapons and the lethality of the weapons and the speed at which vehicles consume fuel and millions of other variables that need to be set so a simulation knows how to perform. That data then gets married up with the hardware and software that is the simulator, and you turn it on and humans start interacting with it very similar to the way you would play a multiplayer online game. They start fighting against the automated enemy and the human manned enemies that are out there. And they test their skills, and their skills are measured, and data about that performance is collected, and then assessments are performed so that when they're done with their mission, they can be briefed on whether they did a great job or a mediocre job or not so great of a job, and shown how they could have done better. And that's part of the learning process, is assessing how well they did. And that cycle happens over and over and over again. So historically, up until this very day, the artificial intelligence algorithms that have been available have only been used in the execute phase. Good old-fashioned AI like knowledge-based system and path planning and finite state machines and all those other algorithms have been used to make assets on the battlefield operate autonomously but somewhat intelligently. And that's it. They haven't been used during the assessment phase or the planning phase or the preparation phase because they don't really fit the actions that are taking place in those other three phases. But deep learning is different. Deep learning is very good at identifying patterns in oceans of data and creating classifications that may classify the performance of a unit as good, bad, or mediocre, for example. They're very good at doing that, and they can turn millions of pieces of data into a single classification of performance, for example. And so in these military simulations, the most current systems that are being built, AI is going to be used in the execution phase, but deep learning and machine learning algorithms could equally be applied during the planning, preparation, and assessment phase to help the humans that are doing all of those jobs. And in this presentation, I want to give some examples of some obvious applications that could be tried right out of the chute. So during the preparation phase, you're dealing with a scenario database that is huge, gigabytes worth of data. And during the assessment phase, you're dealing with collected data, which is probably a couple of times bigger than the scenario database. And there are humans working in both of those areas, and it's a very tedious job to get your arms around all of that data. And there are some opportunities for improvement in how that's done. So here's an example from a battlefield where I've taken a God's eye view snapshot of the battlefield because I wanted you to see dozens of units, dozens of objects, hundreds of objects, and what they're doing on the battlefield rather than thinking about it from the perspective of one vehicle or one soldier. This battlefield can be understood by algorithms like support vector machines, for example. In large country warfare, like what's happening in the Ukraine right now, and like what the DoD is planning for in the future, where two countries engage in large warfare a la World War II in Korea, there is a concept called the FLOT and the FIBA. And these are essentially dividing lines between the friendly and enemy forces. And a human can look at a map and very quickly dash out a line that shows where that FIBA is. That's the forward edge of the battle area, or kind of halfway between the red and blue forces. And the FLOT, which is the forward line of your own troops, or essentially the noses of the soldiers and vehicles that are furthest forward, for example. but it couldn't be done very well by computers until machine learning algorithms and deep learning algorithms came along. And a support vector machine would be very good at drawing these lines in real time and updating them continuously during a simulation or during an assessment. Another cousin of support vector machines, self-organizing maps, can do a similar job where they look at the activities or the presence of objects in different geographic areas and identify areas where all of the objects seem to be engaged in combat with each other and classify that as one kind of activity. And another area where the objects from both sides are present, but they're not directly engaged in combat. And then maybe areas where it's all one side or the other because you're behind behind your own lines, and you have your logistics forces and your indirect fire forces back there. And so this can also be continuously updated in real time as the battle progresses and highlight where the action is happening and where the action might be about to break out, for example. A project we did at a company I worked with was to use autoencoders to group some of these objects together and identify which ones are engaged in a direct firefight right now, which ones are mostly in a defensive posture, which ones are moving in a reinforcement manner, and which ones are resupply and which ones are indirect fire. So just identifying what the activities, not of one object are, but of lots of them operating together. And then there's our friend, the convolutional neural network, which is very good at looking at both still images and videos and identifying what's in those still images or videos, essentially classifying them as, ISR activities or logistics activities or engagements or movement to contact, being able to look at either a still image and tell you what it represents right now, or look at a video and tell you what is occurring in that short clip of video right now. And perhaps generative adversarial networks could be used to take the scenario database that was painstakingly built over hundreds of hours and modify it and create a variation or a new database that sits on new terrain, for example, but that is still doctrinally correct when it sits on that terrain, and bypass repeating hundreds of hours worth of effort to manually reset that scenario on a new set of geographic terrain, for example. Or transformers, which are literally transforming computer-human interaction right now by generating realistic textual conversations between humans and computers and realistic audio conversations between humans and computers. Soldiers on the battlefield exchange data both in textual format and in audio format. And so transformers could support both of those, such as in this example where a UAV pilot is trying to put a weapon on a target and being guided by an infantry unit that is actually an AI, not a human. And that AI can not only give her very cryptic commands, but it can actually engage her in a realistic conversation about how to get the UAV to the right position to hit the right target. So are there any hurdles to exploring applications of deep learning like this? Technically, the hurdles are not really that insurmountable, and they're being jumped in lots of different industries. But organizationally, the DoD and the Army face some organizational hurdles that are unique to the acquisition process. All of the systems that get purchased by the military, including these simulators that we're talking about, go through a formal acquisition process. And that process is summarized kind of nicely in this article by Steve Stark, which I recommend to you. But I want to emphasize that the process is primarily linear moving forward, which has been fine traditionally for buying objects. And there are conversations back and forth to make sure that the helicopter or the simulation gets built and tested and refined along the way. But in the case of deep learning, which requires a huge amount of data to train the algorithms to perform in a realistic way, the scientists who understand how to create the algorithms and the operators who are generating the data that's needed to train those algorithms are significantly separated in both time and organizational location. And so the R&D phase where the scientists reside typically does not have access to these huge volumes of data, which are generated in the operations and sustainment phase by military support operators who are very good at that job and then have access to gigabytes worth of data that typically moves forward into analysis, but does not move backward to the R&D process or backward into the production, engineering, and programming process. And so if you can't put the data together with the scientists, you can't take advantage of deep learning algorithms. So in conclusion, I wanted to point out that there's a significant opportunity to improve both the preparation and assessment phases of military training, and that access to all of the data that happens in the operational phase is a necessary prerequisite to allow that to happen. And the organizational infrastructure to support that and to make that doable needs to be constructed if we're going to be able to take advantage of deep learning the way other industries have. Thank you very much, and I appreciate your attention.